Okay. Hello, everyone. All right, I think everyone can hear me. So, welcome back to your Comp 335 tutorial. This is your third tutorial. So in this tutorial, we're going to quickly review FAs. So I have a couple of exercises on DFAs and one on NFAs. And then we're going to introduce regular expressions. And then there's this part about minimal DFAs. We're probably not going to have time to cover that, so there's already a video posted under the tutorial section for that particular for that material. So if you kind of need some help to do your assignment, you can check that out, and it'll probably be helpful to do that. All right, but so with that being said, let's quickly jump into some exercises. So there's these two exercises that were already in the slides, but then I thought of another one that I thought might be useful. So try these three exercises. So I'm sorry that this NFA, I just made this now. Try these three exercises. I'll give you maybe 1 minute, 1 or 2 minutes, and yeah, and then we'll look at them together. Yeah, so sorry, this says accepted. Okay, so it's kind of been a minute. So let's go over the solutions. So for the first question, it says here that you're given a DFAM with states, an alphabet, transition function, initial function, and set of final states. And it's saying that if the language accepted by M is the empty set, then it must be that the set of final states is empty. So meaning that you don't have any kind of double circles in your DFA. And so at first glance, that might sound reasonable, but in fact, this is actually going to be false. And the reason for that is because if I start with a DFA here, I don't want it to accept anything. So I can make the DFA here that accepts the empty set. So here we clearly know that the language accepted by M is the empty set, okay? And now what I can do is I can just add some final state here and just make it go to the initial state. So this is a valid DFA, right? It has states, it has an alphabet. The alphabet is AB. The transition function is valid because for each state here, there are exactly 2 transitions, one for A and one for B. So all of this is good. There's an initial state, there's a final state. And so there is a final state here. The final state is this guy. However, as we can see, the language accepted by M is still the empty set. Okay, so this condition need not be true. So that's why the first question is false. Okay, now the second question here was to describe the language accepted by the following DFA. We kind of talked about this in the previous tutorial, but so let's just assume that the input alphabet is AB. Okay, and then when you want to try to see what languages or what strings are accepted by an FA, it's always good to list them from sort of shortest to longest. So if we start with the empty string, we see that if the empty string goes into Q0, it's just going to stay in Q0, right? Because there's no kind of, there's no more input to read after it gets to Q0. So then it stops, it halts at Q0. And because it halted in a final state, we're going to accept the empty string or lambda, okay? But now if you have any other string, so if you have anything that starts with A or anything that starts with B, it's going to start, so it's always going to start in your initial state, but then once it reads an A or a B, it's going to go in Q1, and as you know, Q1 is like a trap state, so it's kind of like a black hole, so nothing can ever escape a trap state because it has this self-looping property here. And so that implies that all of the strings that start with A or B, they're not going to be accepted. So I should probably use red. They're not going to be accepted. So then the only string accepted by this DFA here is the empty string. And so as we discussed, I think we already talked about this, but the language accepted by M is the empty string. Okay, now this kind of makeshift example here, where let me just label these guys. So you have this NFA here. So why is it an NFA? Well, there's a couple of reasons. You have a lambda transition here. You also have some states where the transition is underspecified, meaning that, so for example, here, you know what happens when you read a B, but you don't know what happens when you read an A. And then you have transitions that are kind of overspecified. So for instance, Q0, it has 3 transitions instead of 2. So the characteristic of an NFA is that it is either underspecified, overspecified, or it has lambda transitions. Okay, so it has those properties, and so it's an NFA. So now when we're trying to determine if a string, in this case BA, is accepted by an NFA, we have to be more careful because we need to take into account lambda transitions, okay? So what I mean by that is if you were to just deal with this like a regular DFA, and so you would start in Q0 here, and then you would read this B, so you'd read this B and you would go to Q1, and then you try to read an A here, you try to read an A in Q1, but then there's no kind of, when you read an A and you're in Q1, there's nowhere to go. So you would halt, right? You would halt, but your input won't be finished. So what I mean by that is your cursor would still be trying to read A, but you wouldn't have anywhere to go, okay? And so that's a problem because for an NFA to accept a language, it has to, so for an NFA to accept a string W has to finish, so meaning that all of the string W has to be read, and W has to end in a final state. Okay, so those 2 conditions have to hold. So if you were to just read it BA like that, then you could start in Q1 reading the sort of the B, but then you wouldn't finish your input because you would still have the A to read. Okay, so that's why I'm saying you have to be a bit more careful here. And If you just did it straight like that and you determined that, oh no, it's not going to be accepted, well, you're still going to miss a few cases. And the reason for that is the whole point of an NFA is trying to add some Lambda transitions to try to make your life in creating the machine a bit easier. And so here we have 2 Lambda transitions. And so we need to take very good care of considering those Lambda transitions. And the reason why I'm saying that is because it's true that if I was in Q0 and I read the B sort of straight off the bat, then I would go to Q1 reading B. But what I could also do is I could just say BA is the same thing as lambda BA, right? So what I could do is I start in Q0, and instead of reading a B, I'm going to read a lambda. So you're going to see why this is going to help. So I'm going to start in Q0, read a lambda. So now I'm in Q1. So now I'm in Q1 and I've progressed to B. So now notice that instead of reading B at Q0, I'm reading B at Q1. So now that's what I'm going to do. I'm going to read B at Q1. And so this transition tells me to go to Q2. So now I'm in Q2. And now you have to use the lambda trick again. So instead of saying lambda BA, you're going to say that this is the same thing as lambda B, lambda A. So now what you're going to do is you're going to read this lambda here. You're going to go from Q2 to Q0, reading this lambda. So now you're back at Q0 and you're reading an A. So now you're reading this A and you're at Q0. Well, now you can actually use the transition. You don't have to use lambda again to go kind of directly to Q1. And Q1 is now Q1 is a final state. You finished your input. So your input is finished, right? You finished your input and you ended up in a final state. So that means that yes, you're going to accept BA. So BA is accepted. Okay, so this third exercise here was just to make you notice how you have to be very careful when there's lambda transitions. You always have to see if you can use a lambda transition when you're going from one state to another. Okay, so I hope that's clear. Again, if you have any questions, you can always stop me. But if there aren't any, let's jump into regular expressions. So I know you guys talked about regular expressions a bit last week. Here we're going to cover a bit more. We're going to cover it a bit more with some practical examples. But just to refresh your memory, what is a regular expression? So suppose you're given an alphabet sigma, then a regular expression is a string S that is composed of primitive regular expressions, which are the empty string, the empty set, the empty string, and symbols in the alphabet. So your regular expression can be composed of those primitive regular expressions plus any combination, so plus any combination of those primitives using these operations, R1 plus R2, R1 times R2, or this is kind of like a concat, R1 star, and also R1 bracket is just for the sort of sake of completeness. But so if you have an expression, so if I give you the example here, if you have an expression over your alphabet AB where you have primitives, so you have primitives, and then those primitives are kind of combined using these operations here. So here we have some concatenations, we have a plus operator, and we also have a star operator, and of course the brackets. So if we're combining these primitives into more sophisticated expressions using only these operations, then that's going to be a valid regular expression, okay? However, if you introduce other symbols or other operations, so for example, the intersection or maybe a difference or a reversal, so this is no longer a valid regular expression. So you have to be careful when you talk about regular expressions, not to confuse them with sets and not to confuse them with regular symbols, okay? Because they are kind of a separate entity. They're kind of a separate structure. And so there are specific rules that you can only apply to them. And so, for example, students sometimes write, oh, you just take a regular expression and you subtract it from another regular expression, but that's not a valid operation for regular expressions. So that's something you have to be careful about, not to confuse kind of set operations with regular expression operations. Okay, so that's just to refresh your memory on what a regular expression is. Now, what is the point of a regular expression? So remember FAs, so FAs, which are DFAs and NFAs, what were their sort of relationship to languages, okay? The relationship to languages were that they were machines that would accept languages. So we say that a finite automata accepts a language. So remember, it either says yes or no to an input string. Okay, so that's the point of an FA. It's to kind of say, oh yes, this string that you just gave me belongs to the language that I'm supposed to recognize or not. Now, the same kind of thing can be said with regular expressions, but slightly differently, okay? So for regular expressions, if you're given a regular expression R, we say that the regular expression R denotes or represents a language, okay? And the language or the language represented or denoted by R is written L of R. So this is very similar to where you had an FAM and you say the language accepted by M is L of M. Here, instead of dealing with FAs, you're dealing with regular expressions. So the language denoted by R is written L of R, okay? And so how do you, if you start with a regular expression, some arbitrary regular expression, how do you start from that regular expression and then find an actual language? Okay, so for instance, if I have the regular expression A star plus B, how do I know what L of R is? How do I know what the language denoted by R is? Well, you follow these kind of simple steps, okay? So once you see a couple of these are going to be pretty kind of natural. But for now, let's just kind of go through them one by one. So the primitive regular expression, the empty set, if you take the language denoted by the empty set, it's unsurprisingly going to be the empty set. And then if you have a lambda, the language denoted by the regular expression, lambda, is the language that contains lambda, okay? And then finally, if you have L of a symbol, then you can just think of that giving you that language that contains the symbol, in this case, A, okay? So these are for kind of the primitive regular expressions. So now if you try to combine the regular expressions, what happens if you take the language of that combination? Well, if you take the language denoted by R1 plus R2, that's just going to give you the union of R1 with R2. So when I say R1 and R2, I mean the language denoted by R1 and the language denoted by R2. Okay. And then again, the same concept when you have kind of this concatenation here. R1 concat R2, when you take the language of that, it's just the language of R1 denoted by R1 concat the language denoted by R2. Okay, so you can see how there's kind of a one-to-one mapping between the operation in regex and the operation in languages. And then the same thing for the star operator. Basically, L of R1 star, you just take the star operator out. Okay, so now that we've seen these kind of operations, how do we actually apply them? So suppose you're given this regular expression here, R, that has A plus BB sort of concatenated AB star. And I want to know what the language denoted by R1 is, R is, okay? So essentially, I just need to apply the rules that I just covered here. So I take L of R, and so I know that R is just this guy, right? So now I use the third rule where L of R1, R2 is equal to L of R1, L of R2. So this is your R1, and this is your R2, okay? Then to go from here to here, I take the regular expression A and the regular expression B, and I see that there's a plus in between. So I know that if there's a plus, then there's going to be a union in between the languages denoted by A and BB, okay? And then the same thing here, I have a star, so I can just take the star out and apply the star operation, so the star closure to the language denoted by AB, okay? And once we have this, now we can start actually converting these to actual sets. So the language denoted by A is just going to be the set containing A, or the language containing A. And the language denoted by BB is just the set containing BB. And then you take their union, and that just gives you A comma BB. And the same thing here, L of AB is going to be the set AB. And you take the star, so you just get AB star, okay? And then if you want this in a kind of more compact representation, well, actually, this is more compact. But if you want it without the star operations, then you can just say, oh, I take A, and I concatenate it with AB n number of times. Or another string that could belong to this language is I take BB, and I concatenate it with any number of ABs. Okay. So I feel like this is pretty straightforward. You know, you're just applying these operations. So if you're given some kind of regular expression, finding the language denoted by it, you know, you just have to use those kind of conversions. Okay. So now an exercise for you, maybe 1 minute to try this to make sure that it's been well understood, and then we'll go over the solution together. Okay. So 1 minute starting now. All right. So it's been kind of 1 minute. Let's try to go over the solution together. So we're given this regular expression here, and we want to know how many strings of length 3 or less are in L of R. So once you get really good at these, you can kind of straight away determine what L of R is, and then you can quickly answer this. But just for the sake of completeness, I'm going to go over the kind of similar steps from the previous example, just to make sure that everyone's still kind of on board. So remember, if I want to know how many strings of length 3 or less there are, I first need to find what L of R is. So to do that, L of R is going to be equal to L of, then I just write R, so that's 0 or 0 plus 0, 1, and then that's 1 plus 1, 1 star. Okay, so now this is one regular expression, and it's concatenated with another. So I can just write L of that regular expression, concat L of this regular expression. So this guy here. And then here I have L of 0 plus 0, 1. So I know that that's going to convert to a union. So I'm going to get, well, yeah, let me not do that. Let me not skip a step. So L of 0 union L of 0, 1. Okay, concatenated with, well, here I have a star operator. I can take that star operator out. So I can take the star operator out. And while I'm there, I'm also going to apply L of 1 union L of 1, 1. Okay, So that's what I have so far. Now I'm actually going to convert these guys into sets. So I have the language containing 0, union the language containing 0, 1. Concatenated with L of 1 is 1, union L of 1, 1 is the language containing 1, 1, and this is star. Okay. So after that, what do I have? Well, I can take the union here and take the union here. Okay. And then apply the star operator. Okay, so now I'm here. So I'm just applying the union of languages. Now what I need to notice actually is, so I could start writing out the strings. What I want you to notice actually is that 1, 1, 1 star. Well, this is actually exactly the same as 1 star because this is any combination of 1s and 1s any number of times. And clearly that's equivalent to any combination of just 1s. Okay, so that's any number of 1s. So we have this kind of identity. So now we can just write 0, 0, 1 concatenated with 1 star. Okay. And so if you want that to be a bit more compact, you can just say, well, no, I think actually this is compact enough. Okay. So so this would probably be an acceptable answer if you just wanted to know what L of R is. Now I want to know what the strings of length 3 or less are, right? So how do I do that? Well, I can write 0, 0, 1, and then I can concatenate that with 1 star. So I'm not going to write out the operation for 1 star, but just notice that this is going to be 1 to the 0, which is lambda, then 1 to the 1, which is 1, 1 square, which is so 1 square, 1 cube, and so on. Okay. So now I see that 0 is going to concatenate with lambda, with 1, with 1, 1, and so on. But really, I just care about the strings of length 3 or less. So I'm just going to keep, 0, 0 lambda is just 0, 0, 1, and 0, 1, 1. And then the same thing for 0, 1. I'm just going to keep the ones of length 3 or less. But here they're actually repeating, so I actually don't need these guys. And the strings of length 3 or less are just going to be 0, 0, 1, and 0, 1, 1. Okay, so hopefully that's clear. That's how you would first determine what the language denoted by R is, and then sort of an extra part of that question is find the number of strings of length 3 or less. Okay, and just kind of a comment on these types of questions when it's strings of length 3 or less, or sometimes the language can seem very, very complicated, but because you're only looking at strings of length 3 or less, or maybe 2 or less, try not to do too much work, especially if it's kind of like a multiple choice question. Try not to do too much work, because really you're just trying to find those strings of length kind of that are of length that are very kind of small, right? So I wouldn't start going and taking 0 and concatenating with 1 to the 17, right? That wouldn't make any sense. I know that I can do it, but I'm going to skip that part because my goal is kind of a length of strings. Okay, so that's maybe just a tip in general. Okay. All right. So that was kind of a one direction where you're given a regular expression. So you're given a regular expression, and then you want to find what L of that regular expression is. Now, can we go from sort of, I have a language L, and I want to know what R such that L of R is equal to L. So you're going to see that these are a bit actually trickier than just doing FAs or DFAs, NFAs or DFAs, sorry. But we're going to see a trick later on where you can convert an NFA to a regular expression, and that's going to make this procedure a lot easier. But for now, we're just going to stick to trying to use our intuition to try to form a regular expression that denotes the given language. Okay. So my first example here is I want to write a regular expression R. such that the language denoted by R is the set of all strings over 0, 1 that contain 1, 0, 1 as a substring. So the idea here is what you're trying to do, really, your regular expression is also kind of like a pattern recognition. So it's trying to find a particular pattern in your string. And if it does find it, then it says that it denotes it, basically, or it says that it's part of that language, okay? So that's kind of what the intuition is you're trying to do some kind of pattern recognition with your string. So the answer is here, of course, but let's try to reason about this. I know that any string in L of R is going to have a bunch of 0, 1s, and then it's going to have 1, 0, 1, and then a bunch of other 0, 1s. Okay, so my pattern, when you think about it, is it's going to be kind of any combination of 0, 1s, and then the pattern I'm looking for, the substring I'm looking for, 1, 0, 1, and then anything after that. So I don't care what's before, what's after, as long as 1, 0, 1 is kind of recognized. So, well, what does that look like? Well, I know that the pattern for recognizing 1, 0, 1 is just 1, 0, 1. Now, what is the pattern for saying, oh, I have any kind of sequence of strings? Well, that's actually going to be 0 or 1 any number of times. So you can just read this as saying, at this position, I can either have a 0 or a 1. And that kind of choice can happen any number of times. So remember, star is like any number of times, including 0. So that's going to tell me that the pattern to the left of 1, 0, 1 can be any string, okay? Can be any kind of string over the alphabet 1, 0, 1, okay? And then the same thing can be said here. I don't care what the pattern at the right of 1, 0, 1 is, at my sum string is. I just want there to be 0s and 1s. So I'm going to use the same idea. I'm going to have 0 or 1 star. So try to read this plus also as kind of an or, and this star as like any number of times. And this is kind of like an or, okay? So hopefully that's clear. To check, let's give you an exercise. So I want to write a regular expression R such that the language denoted by R is the strings over 0, 1 that have even length, okay? So I'll give you 1 minute starting now. Okay, so yeah, that wasn't really a minute, but I feel like this one might be not so difficult. So let's see if we can do it together. Okay. So what is the kind of pattern that we're looking for here? We want to recognize strings that have an even length. So what you can think of in this case is you can think of a string W as kind of being pairs of bits, pairs of 0s and 1s. So you're going to have pairs of kind of 0s or 1s. And here the first kind of, so I have kind of 4 options for each pair. I can either have 0, 0, 0, 1, 1, 0, or 1, 1. And I know that this kind of exhausts all possible strings of even length. That's because I know that any string of even length can kind of be decomposed in blocks of 2. Okay, so then when you think about it, the pattern we're looking for is any of these regular expressions, and then kind of you can pick 0, 0 or 0, 1 or whatever for this position, and you can do that choice any number of times. Okay, so what I'm trying to get at is that a regular expression here is going to be well, either in a particular position you're going to pick 0, 0 for one pair, or 0, 1, or 1, 0, or 1, 1. And you can pick that, you can kind of do that process of repeating any number of times. Okay. Also, what you could have thought of, maybe, which would also be correct, you could have also thought of something like 0 or 1, and then 0 or 1 any number of times. So that also tells you that you can kind of see how there's a one-to-one mapping. And that's essentially the kind of same idea. It's just saying that the first position of that pair is either 0 or 1, and the second position of that pair is either 0 or 1. Okay? So that's pretty straightforward. Again, if you have any questions, let me know. All right. So that was for that exercise. Then we have another exercise here where we want to write a regular expression R such that the language denoted by R is VWV, where V has to have length exactly 2, and both of these strings are over the alphabet AB. So because there isn't much activity going in the chat, I'm assuming that everyone really gets these really well. So I'll give you 30 seconds to do this one, and we'll go over it in 30 seconds. Okay, so again, let's try to go over the solution together. So what is the pattern I'm looking for here? Well, I know that my string, so if I have a string x in L of R, I know that x is going to be some string v that has length exactly 2, followed by any string over AB, and followed by the exact same string v. So what you need to notice here is that this v is going to match with this v. Okay, so you're kind of matching the two together. All right. So in this case, it's actually easier if you just list all of the possibilities, because my alphabet is only AB, and because here I have length of V exactly 2, it's not that difficult to list all of the possibilities. And those are going to be, well, I can start my V with AA, and then I have to end with AA, right? And then I have anything in between, so we'll get to that in a second. Or I can start with AB, and then have anything in between, and then end with AB, right? Or I can start with BA, and then have anything in between, and then end with BA. Or I can start with BB, and then have anything in between, and end with BB, right? So these aren't centered. Yeah, so that's going to be the idea. So now all we need to do is kind of replace this squiggly line with any string over AB. And so we already know what any string over 0, 1 is. That's 0, 1, 0 or 1 star, right? And so the same idea applies for any string over the alphabet AB. So that would be A or B star. So then I can just replace each guy here by A or B star. Okay.
I have a
So
quick question.
yes.
Wouldn't it also include any combination, like any combination of the ones that you wrote? So like AA and BB, like it could be anything. Wouldn't we have to write that?
Yeah, so so you're meaning, I guess what you mean is something like this, right? Where you take,
Compare any of the first and the second ones, basically. It's not always in that order.
um, what do you mean that's not always in that order?
Like, isn't another possibility like AA and then A
Right.
plus B star and then BB? So that's
Oh,
not specified, but
oh,
it's
no, 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 yeah, sorry, no, sorry to cut you off, but no, because here, the fact that the V and the V here are the same, so that tells you that,
thing, not
yeah,
just
yeah,
okay.
yeah,
Thank you.
exactly. Yeah, no problem. There was another question, what about lambda and either A or B? Um, Lambda and either A or B. Okay, I'm not quite sure what you mean by that. Because if you're saying, because this A or B star, remember, this can also be lambda, right? So then we also cover the case where we have AA, and then AB, AB, and then BA, and then BB. So this case is also covered.
No, actually, for the V part, when you say like AA, AB, or BA or BB,
Yes.
I'm like lambda A, lambda B.
Oh, I see. Oh, no. Okay, that's a great question. No, because lambda A, if you take the kind of length of lambda A, well, that's the length of lambda plus the length of A, and so we define the length of lambda to be actually 0, because when you think about it, lambda is no symbol, right? So it's kind of like you start a string, and then you close the string immediately. There are no symbols in here. So if you did kind of dot length, or if you wanted to find the length of that string, it would return a 0. So so that's why here the length would be 1 instead of a 2.
But isn't the length the cardinality? And didn't we learn that the difference between the empty set and lambda is that one of them has a cardinality of 1 and the other one has of 0.
Yes. Very good, very good. The only pickle there is that this is not a set. This is a string. So it can be confusing because this kind of cardinality operator is the same for sets and strings, but I'm taking the cardinality, or not the length of a string, and so the length of a string is just the individual length of each of its symbols. In this case, lambda is a symbol in lambda A, but its length is 0, so it contributes nothing to the string lambda A. But I do agree that the cardinality of the string, so the cardinality of the set that contains lambda, this is for sure 1 because it has one element. But you can't sort of confuse the set that contains lambda with just lambda itself, okay? Because, okay, is that clear?
Yes, thank you.
Okay. Nilufar, is that also clear?
Yes, thank you.
Yes. Okay. Awesome. Okay. Good. Okay. Very good question. Very good. I'm happy. People are listening. All right. Okay. Good. Awesome. Excellent. Okay. So, but if there are no other questions, we can kind of move on. So, what's the other? Oh, yes. Okay. So, the kind of last concept we're gonna talk about with regular expressions is the idea of equivalent regular expressions. So when are two regular expressions, R1 and R2, when are they equivalent? So by definition, we say that the regular expression R1 is equivalent to the regular expression R2, if and only if the language denoted by R1 equals the language denoted by R2, okay? So essentially what this is saying is that R1 and R2 is doing the same work. It's doing kind of, there's no difference in what the two regular expressions are denoting, okay? So for instance, I have this regular expression, and I want to determine if it's equivalent, so there should be three equal signs here. I want to determine if it's equivalent to R star, okay? So how do I do this? Well, essentially, I just take I do L of this, and then I check if it's the same as L of this. So I want to check the equality there. Okay, so by now, I feel like we're a bit more comfortable with this kind of idea. So if I take L of this guy, so this is kind of one regular expression and this is another, so I can just do the kind of concatenation, L of that regular expression, concat L of the other, okay? And then I have a star operator for regular expressions. So maybe actually I'll emphasize this point. At this particular moment, this is the star operation for a regular expression, right? And now what I can do, because this is kind of L of is like an operator, what I can do now is I can take the star for the regular expression and then I can apply it to the language. So this is no longer a star for regular expression, it's a star for the language. And in this case, it's the language L of R or the empty set, okay? So now that I've kind of transformed this operation into this regular expression operation to a language operation, I can apply it kind of more easily because I know how it works, right? So I have L of R plus the empty set. So again, this is the empty set as a regular expression, but I know that L of R1 plus L of R2 is L of R1, so in this case, this is my R1, union L of R2, okay? And now I'm going to use a set property. So I'm going to use the set property that if I take X and I do union the empty set, then the empty set is not giving me anything else to add to X. So this is just going to give me X. So essentially, I'm not getting anything else, all right? So that's why when I do L R1 union empty set, I'm just going to get L of R1 star. And then here, so here I kind of skipped a step, but L of lambda is the set containing lambda or the language containing lambda, okay? And then I know that for any language L, if I take L and I concatenate it with the set or the language containing lambda, then I'm going to get the language L, okay? And maybe if you're not convinced by that, the reason why is just because if you take any string W in L, you're going to concatenate it with lambda, so you're going to get W lambda, but that's just equal to W. Okay, so essentially, this guy is not doing anything else to the language, so you can just say that it gives you the language L itself, right? So yeah, I should have probably written that here. So this is L of R1 star concatenate the language containing lambda, and then using this property here, I get L of R1 star. And so what has happened? Well, I have that L of this guy. So maybe let me use a different color. L of this guy is the same as L of this guy. And so that means in terms of regular expressions, this one here is equivalent to this one here. Okay, and so that's how we say that the two are equivalent. Okay. Okay, so now to make sure that I wasn't just talking to myself, what time is it? Okay, so now a few exercises just on this, where I want to prove or disprove whether the following statements are true or not. Okay, so yeah, let's just take the rest of the, okay, let's take 1 more minute. 1 minute for you to try these, and then we'll go over the solution together. And then, as I said, oh, okay, okay, maybe I should make, for minimal DFAs, I'm not sure when you're, because it's very strange. In the summer, you guys cover this earlier, but in the fall, it's later. But so whenever you covers minimal DFAs, we can kind of, I can remind you that there's already a pre-recorded kind of tutorial section just on that. Okay, but 30 seconds or whatever, or a minute to do this, and then we'll talk again. All right, so it's been kind of 1 minute. So my minutes are very strange, but let's try to go over the solutions of these questions. I had another one that I wanted to show you, so we'll see if we can get to that one. But essentially, let's do this first one here. Oh, is my my pen is okay. So just give me a second while I fix my pen. So essentially, again, what do we need to do here? We have a regular expression on the left, and we have another expression on the right. And to show that these two are equivalent, oh no. Okay, to show that these two are equivalent, oh, okay, good. Whew. I need to show that the language denoted by this guy is the same as the language denoted by this guy. Okay, so what's kind of an intuition here that I can kind of give you? Well, here we're trying to say that the star operator is kind of distributive. However, if you take, for example, R1 is A and R2 is B, okay? So the left-hand side is going to be A or B star, okay? And what is A or B star? So L of A or B star, that's just, if you say sigma is AB, right? That's just sigma star, right? That's all of the possible strings over the alphabet AB, right? But now if I take the right-hand side, so the right-hand side is going to be A star or B star. So what does this pattern look like? Well, this pattern tells you I want either a bunch of A's in a row or I want a bunch of B's in a row. And this is kind of like an exclusive OR. So I either want a bunch of A's or a bunch of B's, but I can't have kind of both at the same time. And so that's kind of a hint that this is probably not really equivalent to this. And if we check it using kind of L of A star plus B star, well, I know that this is equal to L of A star union L of B star. And I know that this is A star union B star. So notice that these guys, they don't mingle. The A's and B's, they don't kind of intersect, and then you don't get kind of a permutation of A's and B's. It's only going to be a bunch of A's or a bunch of B's. It's not going to be A, B, A, B, A, B. So we can see that these two languages are actually, let me use a different color. These two languages are not the same. And so because the languages are not the same, A or B star is not going to be equivalent to A star or B star. Yeah, I realize this is not the clearest way of writing this, but But essentially, I hope you get the idea. The languages aren't equivalent, and so the regular expressions aren't equivalent. Okay. Now let's do the other exercise here. What does this one say? Yeah, okay, so this one says that you take the pattern kind of R1, so you have the pattern R1, and then the pattern R2, and then you take a star on it. So what does that kind of tell you? That kind of gives you R1, R2, R1, R2, R1, R2, and so on. Well, that doesn't really look like the pattern R1 star, R2 star, because what this looks like is R1 a bunch of times, and then R2 a bunch of times. So clearly I see that this guy has more, it recognizes more strings than this guy. So that's the intuition that's going to lead me to believe that these two are not equivalent. But now I need to prove it with kind of a counterexample. So what's the counterexample I'm going to use? Yeah, so let's say R1 is the regular expression that is the empty set, and R2 is just the symbol A. Then R1, R2 star. So if I take L of this, well, that's going to be L of the empty set A star. So what is that going to be? I can take the star out. So I do L of the empty set A, and I take the star out, and then that's going to, so this is the left-hand side. That's going to give me L of the empty set concat L of A star, and then this is the empty set concatenated with A, the set that contains A star. And so the empty set concatenated with any language, that's the empty set. So I have the empty set star, which I hope you remember is, so if you don't remember this, just consult the tutorial notes. But if you do remember, hopefully you know that this is, the empty set star is equal to the set containing lambda, okay? So this was the left-hand side, right? Let me make this, can I zoom out? Yes, okay. And then the right-hand side is going to be what? Well, the right-hand side is going to be L of, so I'm still using this guy, L of R1, R2 star, star, that's L of the empty set star, A star. So that's, so sorry I'm going a bit fast, I'm just assuming that these are now a bit easier for you. So now that's going to give me L of the empty set star, L of A star. And then I can take the star out, kind of, so I have L of the empty set star, concat L of A star. And then what is this going to be? That's going to be the empty set star concatenated with A star. And so this is going to give me A star, just because this is the set containing lambda. And so clearly this guy, this set, the set on the right-hand side is different from the set on the left-hand side, i.e. that is, whoops, these two are different. And because these two are different, this implies that the regular expressions are not equivalent. Okay, so that's what that implies. All right, so so then you would be able to show that both of these were false. And then, so I don't really have time, do I? No, not really. But I'll give you this one kind of as an extra exercise if you're bored. R1 plus R2 star, is this equivalent? So I think you might actually find this, come on, okay, sorry. You might find this one in a book as well, but I think it's nice to get you thinking. So are these two equivalent? So I'll leave this as an exercise. The quiz today doesn't, no, it's not going to be on regular expressions. So maybe try not to focus on this too much for now. For the quiz today, you know, try to look at NFAs and NFAs to DFAs. The tutorials that we posted last week should be helpful for those. But for next week, or for kind of dealing with regular expressions, maybe try to think of this guy as kind of an exercise, and it might help you if there's those kinds of proofs in your assignments or your quiz. All right, So yeah, I can stop here. I'm not sure if there are any questions. So now I'm going to ask if there are any questions and wait awkwardly. Okay, so are there any questions? No, there are not. Okay. Okay. that's that's not exactly the question that I was looking for, Brian. But thank you. I appreciate it. I hope these tutorials are I hope these tutorials are helpful. And I hope the extra recordings. I know it's very annoying because there's recordings for the lecture and now there's 2 recordings for the tutorials. I'm really sorry that we're kind of like, it's really annoying that there's so many recordings, but just try to use the tutorials, like if you're getting stuck, then try to use them as extra help, okay? If not, you know, don't like, if you have like 4 or 5 courses, then, you know, I understand that you can't really consult all of them. But yeah, okay, so yeah, as Jenna said, you know, we're just trying to give you as much as we can. All right, okay, so that was a funny comment. All right, so yeah, I hope that was helpful. I hope you guys have a great week. Good luck. Good luck in your quiz and in your assignment. And if you have any questions, you know, just shoot the TAs an email. You can CC all of us, and one of us is bound to answer. The professor as well is actually really good at answering questions quickly. So yeah, so yeah, so that's it for me, guys, and take care. All right, see you.